Okay, so the last concept in chapter 6 is the theorem of the primitive element. And we're going to build up to that. So I'll remind you what that is when we get there, but we're building up to that. So our first lemma is the following. If P of t in K adjoin T, again in this class, unless otherwise specified, K is always a subfield of C. If this is irreducible, then it doesn't have multiple zeros. So it only has simple zeros. So all zeros happen with multiplicity 1. So if we were to look at the zeros in C, all the zeros are unique. You have exactly the degree of P many zeros, and there's no repeats. Okay. So proof of this fact, if P of T has a multiple 0 in C, then we can write, ooh, that's terrible then. Let's fix that a little bit. Then P of T is, well, it has a 0 of at least multiplicity 2 if it's a multiple 0. It might be more. It might be that the 0 is a multiplicity 10. It doesn't matter. We can at least factor out a t minus a squared from it, at least. Okay? And this is a factoring not in K. P is irreducible, so it doesn't factor in K adjoin T, but this is a factoring in C adjoin T. Then what we're going to do is we're going to look at the derivative. So P prime of T, by the product rule, the derivative of this expression is the derivative of the first guy, so that's twice t minus a times the second, plus the first times the derivative of the second. All right, cool. So what do we have now? Well, we can pull out a t minus a here. I guess we pulled one out, so there's only a t minus a in the second one. Okay, so P prime of t and P of t share a factor. When you go to the big field C of t. But P prime of t is actually an element of K adjoin T. Why? Well, when you take the derivative, all you do is you multiply by whole numbers, right? You bring the exponents down and you decrease an exponent. So if I multiply by rational numbers, integers even, I stay within the field because all rational numbers are a subfield of all subfields of C. Okay. All right. So what? Well, P of t and P prime of t certainly share a factor in C adjoin T, but actually more is true. Um, uh, they, how do I want to say this? And A is certainly therefore algebraic over K because it's the root of P of t and it's also a root of P prime of t. And so P of t and P prime of t have A as a root. And what do we know about the minimal polynomial? We know the minimal polynomial of A has to divide any polynomial that has A as a root. So in fact, the GCD of P and P prime has degree at least the minimal polynomial, which is positive, at least the degree of the minimal polynomial. But P is irreducible. So in fact, it actually has to be the minimal polynomial. But P is irreducible, and so the GCD of P and P prime must be P because that's sort of the largest and the smallest it can be. But this is impossible. The degree of P prime is the degree of P minus 1, which is strictly less than the degree of P. So it cannot be that they share a factor. Sorry, this isn't written all that well, but the idea is here. Okay. Oh, shoot, I didn't write my contradiction. What would we contradict? Well, um, P has no multiple zeros. And this seems kind of weird, a weird condition to look at, and it might come from left field. Like, why are we doing this? And there's this when you do Galois theory over arbitrary fields, not necessarily subfields of C, you have to worry about a separability criterion for the fundamental theorem of Galois theory to work, and this fact doesn't hold for all fields. Okay, so it's something that holds for certain fields. In fact, it will always hold in characteristic 0, which is where we work. But you do have to be careful in characteristic P.